Hello everyone. Welcome to LeetCode discussion of contest 479. Let's start with the first problem. The first problem says that we are given integer array nums, and the binary reflection of a positive integer is defined as the number obtained by reversing the order of its binary digits. For example, 4 in binary. For example, 4 in binary is represented by 100, so its reverse is 001, which is 1 itself. Now, for each numbers, convert them into binary, get their reverse orders, and the reverse orders are our new criteria for sorting the array. Now, if there is a conflict, that is, the two numbers have same reflected values, like some other number, like for example 8. 8's binary representation is 1000, so it gives 1 again. So if there is a conflict of same reverse value, then in that case we would compare the two numbers using the previous number, that is 4 and 8 would be considered 4 is smaller than 8. Okay, so what do we need in this problem? We need to create a comparator function. So let's start. What do the comparator function demand? Okay, some basics about the comparator function in C++. If you want the array to be sorted in ascending order, you just need to return like this, where you have taken two parameters a and b. This particular sign in middle represent the order in which you want the two numbers to be sorted. Let's say we have A and B. A and B represents the index I and index in J values, which are A and B respectively. All right. Let's say we have two index and we have a conflict or question that whether to put the value at index I first in the sorted array or index J first in the sorted array. And what are the values? They are A and B. Then this particular condition, if it is true, then the number will be swapped, else it won't be swapped. So this is it. If you want the number to be sorted in ascending order, return a smaller than b, else return a greater than b. Alright. So what do we need? We need binary representation. So we need the binary representation of our array. Alright. Let's denote it as a function named binary, which will return the binary uh, reversed value of our string. Alright, and the first number is a. We want the binary representation of a, then binary representation of b. Alright. Now, what is the criteria of checking if b1 is equal to b2? That is, binary representation is same. Then we compare the initial numbers, that is a smaller than b. Else, what is the criteria? We just return b1 smaller than b2. Compare according to the binary values. Now, this binary function, which returns the uh, binary reversed values of our given value. Alright. Let's name this particular function static. So we can use it inside a class function. Similarly, this function, we want the binary reverse orders. Take a string. Now, while a is not equal to 0, just push back 0 plus a modulo 2. Alright, and a divided by 2. This gives us the binary representation in sorted order. Now for num, the num represent binary reverse string in decimal. So what happens with the number? This 4 is actually 100, and uh, what is inserted inside the string? First 0 is inserted, then 0 is inserted, then 1 is inserted. So it is 011 inside the string. Alright, now for 0th index, we want it to be 2 to the power the maximum number of bits. So start from the 0th index. We want for each number that is 1 inside our string to be st.size minus 1 minus I. That is for 0th index, the maximum possible bit. For the first index, the second maximum possible bit. Now return this particular value now. Okay, we have not sorted the string till now. Sort it using the new comparator function. Alright, and then return this nums. This is it. Let's move to the second problem now. So the second problem says that we are given an integer n. We need to find the largest prime number that is smaller than equal to n and can be expressed as sum of one or more consecutive prime numbers starting from 2. Alright, the consecutive prime numbers starting from 2. So the first prime number starting from 2 is 2 itself. So 2 is the first value. Then 2 plus 3, it is 5. Then 2 plus 3 plus 5 plus 7, it is 17. Similarly, going on, then after 7, 11 appears, then 13 appears, and so on. All these values, the maximum value which is prime and is smaller than n, we need to return that value. So what does the question demands us? Question demands us to calculate all the primes. All right. Now, iterate over all the primes and calculate their prefix sums because those are the values that are contender for our answer. Now, if that prefix sum value is prime itself, then uh, the maximum satisfying value that is smaller than equal to n, that is our answer. All right. So this is majorly a implementation problem where you need C to implement how to calculate prime number. Let's move on. Let's move forward towards implementation itself. So what do we need? We need two vectors is prime and prime to store all the prime numbers and check if a number is prime or not. Or you can just do the work with is prime vector itself. Alright. Now the sieve part, what is the maximum value for which we need to calculate it is a prime or not? It is n itself. Alright. Because we want numbers smaller than equal to n. So create a vector of size n. Initially, let's say that all numbers are prime, and then the numbers that are not prime, we will assign them as 0. Alright. Starting from 2, which is a prime number, iterate to all its multiples. If this I itself is not prime, then continue. Right. Else iterate to all its multiples a plus equal to I and say that it is not a prime number. Alright. Now the current sum represents the prefix sum up till ith index and we want the answer. If there is no answer, assign it as 0. Alright. Now iterate to all the prime factors or all the primes and calculate their sum, prefix sums. So start from 2. What is the criteria for a number to get added in sum? It must be prime and it must be smaller than equal to n. Alright. If the current number is prime, then add this to our prefix sum. If sum is smaller than equal to n, and what is the criteria to assign it to answer? It is the current sum is prime itself. Right. Current sum is prime itself. Then answer is equal to sum. Alright. At the end, just return answer. Okay. Problems of long law. Assign everything as int long law. Okay. A typo. J is equal to I plus I, and it passes all the test cases. Alright. Let's move to the next problem. Okay. So let's move to the next problem. We are given a positive integer HP and two positive one indexed arrays, damage and requirement. There is a dungeon with n traps from 1 to n. Entering room I reduces your health points by damage I. After that reduction, if your remaining health points are at least requirement I, you earn 1 point for that room. Let score J be the number of points you get if you start your HP points and enter room J in this order. Return the integer score 1 from score 1 to score n, the number of scores over all starting rooms. Alright. Okay, so what do problems say? Problems say that we are in a dungeon where the dungeon is represented by two arrays. The first array represents the damage point and second represents the requirement. Let's say the first point is D1 and the first requirement point is R1. Similarly, second damage is D2 and second requirement is R2 and so on. Alright, what happens? A person starts from a particular index, let's say first index, then he initially has HP health points. Alright, initially he has HP health points. Now he go to the first dungeon and he gets a damage of D1. So its health point is uh, HP minus D1. Now this HP minus D1, if it is greater than equal to R1, then that person gets 1 point. Else he do not. Alright. Now for each starting values, let's say the person starts from index I, then index I stores that if the person starts from ith index, how many points he can earn. Alright. Now, let's say we are currently at ith index. Alright. So, how many j index satisfy the criteria of gaining a point? Alright. If he is at, let's say we created a prefix sum of damages. Then, if starting point is I, all the points that give point, uh, all the indexes that give one score to our player satisfy this particular condition. What? HP, that is starting point, plus prefix at J. Let's say J is the point that gives us point score. J is the index that gives us score. Then prefix of J minus prefix of I minus 1. This gives us the total damage inculcated in traveling from I to J. Alright. This should be greater than equal to R of requirement of J. Alright. Let's uh, what is variable and what is fixed. Let's say prefix at J is variable because we do not know which particular index gives us the point if we are starting at I. Alright. So take all the terms having J in one side. So prefix at J minus requirement at J is greater than equal to HP plus prefix at I. Alright. Now let's say we have a suffix of uh, prefix at J minus requirement at J so far. Alright. Then we need to calculate all those values that are greater than HP plus prefix at I minus 1. Alright. This gives us all the points that gives us a score starting from index I. And how can we calculate this? We can calculate this using binary search. So let's move to the implementation. Okay, so really sorry for uh, uh, the wrong sign used previously. Here, there should be minus sign because it is a damage we are inculcating. Okay, in HP, we are having a damage of prefix J minus prefix I minus 1. And this particular new health should be greater than equal to requirement of J. So our equation transforms. It just open this minus sign. So this is minus and this minus into minus is positive, and bring all the j's to one side. So it gives us the equation HP plus prefix at I minus 1 is greater than equal to requirement at J plus prefix at J. Okay, so how to calculate this particular thing? Let's say we are at a particular I and we want all the j's that are greater than equal to I and satisfies this equation. So it is a binary search problem using PBDS. All right. So we have a set of all the numbers in which we want to find out uh, all the numbers that are smaller than this particular term. All right. Okay. So let's move forward. That are smaller than this particular term. All right. Let's move forward to implementation part. So I will just bring all the templates required for PBDS. So let's start with implementation part. So n is the size of our array or number of dungeons. Now create a prefix sum for damages as discussed earlier. Let's have a one based indexing for prefix sum. Prefix sum at I my plus damage at I minus 1. Alright. Now create a PBDS. Also have an answer to calculate because we want the sum of all the values. So create a variable answer. Now starting from n, go up till 1 insert this particular term. What do we want? We want all the requirement at j.
That j. All right. So insert this term. Prefix is 1 based indexing. So prefix at sum at I plus requirement is 0 based. So requirement at I minus 1. All right. And just insert the index so that there are no, there are cases for duplicate elements not being uh, unified. All right. Now calculate the term we needed, order of set or order of key. What was the term we calculated? Prefix at I plus HP. Prefix at I minus 1 plus HP. And just insert underscore max. Why? Because we want all the values that are smaller than equal to this term. So they must be smaller than int max as well. All right. So it gives us all the values that are smaller than equal to this term. Then answer plus is equal to val, and at the end return answer. Okay, we must make it a pair.
So let's discuss the fourth problem statement now. The problem says that we are given an undirected tree with adjacency edges uh, given as ai comma bi, where there is an edge between ai and bi. Now we are given a list of good arrays, that is the green one or are denoted by 1 in the good array, and uh, they just mean that they are good, and 0 means that they are bad. Define the score of a subgraph as the number of good nodes minus the number of bad nodes in it. What does a subgraph mean? Subgraph is just a connected component, all right? Like take it is a connected component of a tree, and it is a subpart of a tree, like 0, 1, 2. Now 1 comma 2 is a subpart of a tree with 0 removed, and it is connected in itself. All right, so it is a subgraph. Just it is a subset of tree with a constraint that it is connected in itself. All right. Now for each node I, we want to find the maximum possible score. What is score defined as? It is the sum of good nodes minus bad nodes for any connected subgraph that contains I. All right. So let's understand the problem statement well. What are we given? We are given
A graph which consists of some good nodes and some bad nodes. Let's say there is an edge between these two nodes. Now, if this particular node is green, that means that it is good. All right. And if it is red, then it means that it is bad. Now, green node contributes +1 to our answer, and red node contributes -1 to our answer. All right. Now, for any connected component that includes a given node I, we want to compute the sum of good nodes minus bad nodes. So, is it possible? Okay. So, what is the n square approach for it? All right. In n square approach, we can just start from each node. This is just a brute force code. We will try to optimize it. All right. What does the brute force intuition say us? That start from a node, go to its neighbor. Now, if a neighbor gives positive value, All right, let's say the depth of neighbor subtree up to which it gives us positive value. All right, positive value, or let's say maximum value. That depth should be included. That is the subset that gives us maximum value from its neighbor. Let's say this is the green node, and its second subtree, which is denoted by this particular node, its subtree. The maximum value its subtree gives should be counted in the score of this particular node. Now, how to calculate that? It's a very famous problem. Like, we can keep uh, DP arrays at each node. If you have done even simplest problems of CSCS DP on trees, then uh, it is simple to understand. Otherwise, just try 1-2 problems from CSCS of DP on trees and retry this problem. All right. So we calculate the DP value at each node for its subtree. The DP value says that if we consider the node subtree, what is the maximum value we can get? All right, create a DP. DP at I node says that it's subtree. For now, we are not given the root, so let's take 0 as the root. All right, nodes subtree maximum value. All right, for contribution. Now, for a given node, let's say node, go to all of its children, all right, not its parent. How to calculate this DPI? I'm stating the recurrence relation. For all its node that are its children, sum of children, max of 0 comma DP of child. All right. For all its children, go to all of its children. If it contributes positively, it is good that we get some positive number added to our maximum value. If it is negative, no need to consider it. All right, because it reduces our maximum value, and this node need to be included itself. So if this node is good, then add uh, 1, else add -1. So it is easy to calculate DP at I using this recurrence. All right, now, but we had an assumption in starting that our root node is 0. All right, so we can calculate the answer for root node using this. So what was our n square approach? Just run this DP on each node. But can we run n square solution? No, it's not possible because n is 1e5. So what to do now? We need to optimize this one. All right. Let's say we have already calculated this DP array. Let's try to find out the relations between the nodes if we have already calculated the DP array. The answer for 0 is DP at 0 itself, all right, because we have taken it as root and calculated. Now, how to calculate the answer for 1? All right. The DP at 1 will always be a contributing factor because this node is included in it, this node is included in it. But the part which says that this is also a subtree or children of uh, this particular node, let me remove all the explanations for better understanding. All right. We had subtree here, we had subtree here, and DP at this red node is the sum of contributions due to this, and this node itself, but it is not due to this particular subtree. All right, when we make this particular node a root, this green node also becomes a subtree. So how to calculate it? All right, if we take DP at node, or let's say green node, which was initially 0 according to our assumption, minus dp at red. All right, the contribution in this particular node, considering this red node as a subtree. All right, if we remove this, then only the contribution due to this part is left, and we can use this to calculate the dp value or answer value for this node. Okay, so what did we tell? What did we analyze? For children of a node n, for children c of a node n. All right, contribution is equal to dp at node minus dp at neighbor, or because dp at neighbor was in itself taken as max with 0. All right, why? Because we are not considering negative terms here, max with 0. So this is it. Now if the contribution is negative again, then no need to consider it. All right, take max with 0 again. So this gives us the contribution due to above subtree, and using this optimization we can solve. What did we do? In O of n, we calculated the dp value for each node. Now, keep on iterating from node 0 to all its children, calculate the contribution due to the part which was not calculated above, just because we assumed that root is 0, and later on add that value inside the contribution of that node and just find the answer for each node. So let's move to the implementation part. So what did we need? We need two DFS. The first DFS, node and parent, along with good to calculate the DP values. All right. We need adjacency list. Name it as graph. We need two vectors, answer and DP, as mentioned in our approach. The first DFS calculates the DP value. Now, if this node is good, then DP of node equals to 1. Else, it is -1. Alright. Now, contribution due to its children. Alright. Now, if the neighbor is parent, continue, because we were considering only children. First apply DFS so that the DP values are filled for the children. Now calculate DP at node is equal to plus equal to max of 0 comma DP at neighbor. All right. This is it. We have calculated the first DP. Now DFS 1 node and parent, along with the contribution from the parent value itself. Now what does the answer at node represent? It is represented by dp at node, that is its subtree contribution plus its parent contribution, which is val. Now iterate to all its neighbor. If neighbor equals to parent, continue. Else DFS 1 of neighbor node. Now new value. What is the new value? We calculated it as max of 0 comma val plus dp at node minus max of 0 comma dp at neighbor. What is it? The contribution due to the current subtree which we are going to, subtracted from dp of node. Okay, contribution due to this subtree when we are moving from green node to red node, subtracted from the total contribution or total value at green node. All right, and if it is uh, like negative, then max it with 0. Now all the assigning things, we want a dp of size n, we want the answer of size n, we want a graph or adjacency list. Now iterate over the list given to us, edges, build the adjacency list. We are not using our template, so push. At the end, run dfs. For the first dfs, 0, -1, good, because parent is -1. Now for the second dfs, 0, -1, and what is the initial value? Because no parent for uh, 0th node, so no contribution, which is at the end, we just need to return answer value. All right, this is it. All the best for upcoming contests.